Respected dignitaries, participants from the various institutions, and my dear colleagues, very good morning to one and all. I, Rambabu, Assistant Professor, Department of EEE, delighted to welcome you all on behalf of Gates Institute of Technology for Day 2 of the 5-day Faculty Development Program on Emerging Trends and Challenges in Renewable Energy Systems, organized by Department of EEE, Gates Institute of Technology, Gutti. Now, I would like to request Ms. S. Resma Madam to give brief introduction about the Day 2 speaker of this program.
Thank you, Rambabu sir. Now I take the opportunity to introduce today's our speaker, Dr. Dastagiri Reddy sir. He has completed his PhD from NIT Tiruchi. He has done his postdoctorate from National University of Singapore. Sir has been working in NIT Karnataka from 2019 onwards. Sir has published 12 patents. To his credit, Sir has published more than 30 papers in international and national journals and conferences. Sir has completed 8 sponsored research projects. Now I request Day 2 speaker Dr. Dastagiri Reddy sir to take over the today's session on topic smart integration of renewable energy technologies at stand-alone AC motor microgrid. Thank you, sir.
Thank you, ma'am. Thank you for the kind words. Ma'am, I don't see any participants, like how it works here.
Sir, your voice is low, sir.
Madam, I don't see any participants in the call. Generally, how it works?
Sir, actually the participants are in YouTube, sir.
Okay, but how they communicate if there are any questions?
Sir, actually one team is there here, sir. If any questions rise from the participants, we are collecting the data and we send to that data to you, sir.
Okay, okay, madam. So
We
live
will,
interaction is not possible.
yes, sir. We will send that questions to you, sir.
Sure, sure.
Okay, thank you, sir.
Yeah, I hope my screen is visible.
Yes, sir. Visible, sir.
Yeah. Hi, good morning, everyone. So, myself, Dr. Dastagiri Reddy, and this is my profile as already introduced by Madam, and I will skip this. So, basically, we at NITK are working towards majorly on electrification of roads, electrification for e-buses, electrification for charging stations. So these are the areas that we are working on. Just to give a brief introduction about our lab and our activities. These are the summary of my contributions at different locations. So NIT Trichy, NUS Singapore, and for a short duration of 2 years I worked at ABB as well. Then here at NITK. With a team of 3, we created a lab called E-Mobility Research Lab. We are working on various aspects of e-mobility. He is Dr. Prajuf, PhD from IIT Bombay. He also worked in industry at L&T Technologies, Bangalore. And Dr. Kishan, whose expertise in wireless charging, also did PhD at NIT Trichy. So, team of 3, we started working towards e-mobility areas. The first concept we proposed is a charging station. So we know there is a huge business for charging station, but fortunately, the level 1, level 2, level 3 DC charging stations are required. But where we can install them, in what way we should install them is what our focus. Currently, if you see any charging stations, we are buying some set of chargers and installing in certain locations. But you know, any charger consists of a rectification stage and a DC-DC conversion stage. So that is where we proposed. So why to have multiple rectifiers and DC-DC converters purchased and placed in operation? Why can't we have a common rectification stage? So that was our proposal, and we got a grant of 60 lakhs from the Department of Science and Technology, and we have filed almost 3 patents related to this topic. So the advantage is what you get when you have a common rectification stage. So first thing, people question reliability. So why having a common rectification stage will have an issue with reliability issues? So the answer is, we don't go for non-reliable converters or whose reliability is a question mark. So we thought of going towards 12 pulse thyristor or diode bridge. Then people will question, like, if you use that, what about passive filters? So our invention is there to eliminate passive filters required for 12 pulse converter. So in this entire topology, if you see the 12 pulse rectification stage, we are eliminating the passive filters, and that's how we can meet the grid code as well as the power density requirements of a charging station. Then in the downstream, all the green color boxes, we proposed reconfigurable converters where you can use it as an AC charger or DC charger. If at all you will increase the power rating, you can increase the power rating by operating the parallel, as shown here. So, and when it comes to renewable energy, previously you have only one option to integrate at the AC bus. Now we propose to have two buses, one is AC bus and one is DC bus. So renewable energy integration will be easier because the two different voltage levels are available for you, and hence it will be easy for any integration of renewable energy. So that's advantage. Coming to other inventions that we are working towards, for example, you have a portable TV, and you want to convert that into smart. So you bring in Amazon Fire Stick or Apple TV setup box or something, and you make it smart. So similarly, what we thought is, why can't we do the similar thing for existing EVs? So the existing EVs have a limitation of charging power, onboard charging power. If at all you want high charging power, you go for DC charging station. So then what we thought is, so why can't we convert every
Hello,
car?
sir.
Yes, sir.
Sorry to disturb you, sir. Sir, some disturbance is there from your side, sir.
Um, like the noise, is it fan noise or something?
Your background, some disturbance is there, sir.
Okay, so
I think fan sound, I think so, sir.
okay.
Maybe. Thank you, sir. Sorry for the disturbance.
Okay, I hope it is fine now. Is it better?
So, yes, sir. It is better, sir.
Okay. So what we thought is, so why don't we convert every car or every electric vehicle into a smart charger itself? So we propose to utilize the motor drive, and we are not doing any modification to that. We just introduce a coupling box, and that can make your car into a smart charger. So that is what another invention we filed in as a patent, and we are in commercial discussion with some companies. Right, coming to other invention, what we propose here, we have seen, like, in the market there are two-wheelers coming up with two batteries. Instead of single battery, they are coming up with two batteries. Now, when you have two batteries, how can we go for integrated charging? And that is where we proposed another solution, which has been already patented and granted, and we are in discussion with some two-wheeler companies. Then, as I told you, when you want to integrate renewable energy to the DC grid, which is very high, or in other words, or other scenarios, you have your solar PV panel at your home, and you need to charge a two-wheeler which is of low voltage DC. You need to charge your four-wheeler which requires a high voltage DC, and you need to power your home. So basically we need like 4 ports. So we proposed a single 4-port converter which can do the all the above things. Like you can take your solar power, you can integrate your grid, and at the same time you can power your two-wheeler and you can power your four-wheeler as well. This is also a patented concept that we worked. And then on the other hand, working towards high-end electric vehicles about to launch in the market. So some buses, trucks, and high-end four-wheelers are now looking towards having a 800 volt battery. So now getting 800 volts from single phase power supply is a tricky job. So we thought, how can we do integrated charging which can suit such cars or trucks where you can boost 230 volt AC to 800 volts DC with single conversion stage. And that is where another invention comes into picture. So this topology can support almost every category of vehicle, 400 volt category of vehicles or 800 volt category of vehicles, and that is where another invention comes into picture. So now in the wireless charging, yes, we have multiple stages. As we all know, we need to convert AC to DC, then DC to high frequency, then the coil, then coil transfers the power to another coil, then you need to convert back to DC, and then a DC-DC converter. So our invention starts with how to reduce the number of conversion stages, which has been patented and granted. And then, as I told you, if you have 400 volts or 800 volt system, then you need one coil setup or two coil setup, like two pairs of coil. So now, how to do that? How to handle that? And that is where we proposed a simple solution where you just switch over from one mode to another mode by using a single uh, nominal switch, or maybe I would say a contactor based switch. I mean, you don't need high frequency switch. So you can connect to one, you will get 400 volts. Connect to the two, you get 800 volts. So current doubling and voltage doubling can be easily made by simply switching over from one to two. This is what another invention we got it, and it is also published in IEEE Transactions and Power Electronics. And one more invention what we proposed here was, why to have two sets of coils? Why can't we do that with single set? And that invention is not published, but we filed as a patent. So overall, these are like few areas we are working towards e-mobility. And good thing is, we are in commercialization stage. So we are about to discuss with some companies and taking this to market. So these are few areas that we are working on. So moving to today's topic, that is how to integrate renewable energies into a smart AC grid, right? So this work has been carried out at a National University of Singapore when I was doing my postdoc, which was funded by EMA and NRF, that is Prime Minister's Office. So before jumping into the topic, I would like to just give a brief introduction so that we all can be on the same page. And of course, you can relate like what I'm going to talk about. So basically, we can categorize all the grids into three categories. One is a strong grid, a weak grid, and a smart grid. Okay. So I hope everybody know what is strong grid. So strong grid, basically you have a voltage source and I would say a negligible impedance, very small impedance, which is like more or less close to an ideal voltage source. So what is ideal voltage source? We don't have ideal voltage source in practice, but I would say it is more or less close to ideal voltage source. We know that what is the meaning of ideal voltage source. So the meaning of ideal voltage source is irrespective of any load that you connect here, the voltage shape frequency and theta. So these are the three major things that are required. Voltage, frequency and phase will not get disturbed much. So whatever may be the load here, the voltage, frequency and theta will make like more or less constant. Okay, so they maintain all the things can be nearly constant, and that is where strong grid comes into picture. If this is the case, you can apply a non-linear load, a linear load, you connect to another grid, it doesn't matter. These things are does not get influenced. They can't be influenced. You can't influence them. So cannot influence these three parameters. So what about weak grid? Weak grid, we can say a voltage source with a reasonable amount of impedance in series with it. So now what will happen when there is a, let's say, grid, and this is the PCC, and you start loading with different loads, uh, the voltage, frequency, and theta can somehow get influenced. You can influence them, or you can disturb them, or it is getting disturbed by different loading condition. How is that? So as you know, whenever there is a current flowing here, there is a drop. Okay, there is a drop, and if there is a sinusoidal current, there is a sinusoidal drop. If there is a non-sinusoidal current, you get a non-sinusoidal drop here. Okay, so that means if you have a sinusoidal voltage at the source, but because of some current drawn and because of this so-called source impedance, that I into Zs will result in some weird shape voltage, and this minus this will result in a non-linear voltage which is appearing at the PCC, and that will disturb the entire grid. Okay, so that's the problem with the weak grid. You can also define strong and weak by using the so-called short circuit capacitance, SKVA rating. Okay, short circuit capacity or short circuit current, what is maximum installed power that is allowed in that particular location, is decided by the so-called short circuit capacity, right? So peak rate means you have less short circuit capacity, right? In other words, but what is smart grid? Smart grid is basically something that you can control voltage, frequency, and theta. So all the three can be controllable. So how can you get that? So how can you control them? So you can control them by using a voltage source inverter. You can control them by using a voltage source inverter. So basically what you need is you need a voltage source inverter whose modulation index, if you vary, you can control the voltage. If you change the frequency of the modulation index, you can change the frequency of the grid that you are going to create. Okay, and if at all you want to change the phase, you can shift the modulation index accordingly. That will be reflected. So now for example, if at all you want to go and connect this to a strong grid, what will you do? You use something called PLL, get the voltage of the grid, frequency of the grid, and theta of the grid, and you use this information and give it to voltage source inverter, and you control them so as to match the voltages, frequency, and theta accordingly, right? So accordingly you match, then you can happily integrate with the strong grid and keep exchanging P and Q. You can exchange P and Q because you can able to control V and theta. But now if you want to integrate a weak grid to strong grid, then there is a problem. So what is the problem? This weak grid uh, voltage, if at all, if it is a diesel generator, let's say it is a diesel generator, I'm considering this as a diesel generator. Now in diesel generator, you can control V, you can control frequency, but you can't control theta. Can't control theta. So then how to do that? Now, how can you adjust VF theta so as to go and integrate with the strong grid, right? And that is where some tricky questions comes into picture, and that is what we are going to address in this, right? So for example, if there is a battery connected to this voltage source converter, that means energy storage used here, right? So now if there is a strong grid trip, the strong grid has been tripped. Now all the three are connected somehow. All the three are connected somehow. Now who will take care of maintaining the grid? Who will behave like a master? Who will behave like a slave? Who takes care of grid forming? Who will takes care of grid following? Okay, so grid forming should maintain voltage and frequency. Grid following should maintain the required P and Q. So these are the things that are very important for AC microgrid. When there are two things, just a grid and a converter, it is very easy. You can do that by using a simple PLL and control. But when you have like three things, with all these categories, strong grid, weak grid, and smart grid, then the issue is if something goes wrong with one of them, then who will take over which responsibility? And that's the biggest question mark, and how to do that. And that is what we are going to address in this particular session, right? So we proposed a solution, and that is what I'm going to discuss. There may be other solutions available in the literature. You can always go through them as well, right? So why we need all this? Because there is a huge half grid market. So if you have a grid, strong grid at your location, you don't have to worry at all. But there are so many industries which are off grid. For example, um, marine industry, right? Oil rig platforms, then mines, and this military applications which are quite far away from the cities. So all these markets require power supply, and you can't lay a transmission line to extend your existing grid to that particular location because of so and so reasons, like the platform may be flat, not flat enough, or the cost may be high. So whatever may be the reason, so that is where you need a standalone microgrid. You need a standalone microgrid. And again, when you say standalone microgrid, you can't expect a reliability without having multiple renewable energies of different characteristics should come together. So only then there is a possibility of providing a reliable power supply. And that is where there is a huge need of research related to standalone AC microgrids, right? So uh, the motivation behind our project was, in Singapore, in and around Singapore, there are so many islands. The number is somewhere around 17,504 islands were there, are still there, and 922 islands are not even occupied. And there's no activity going on because there is no power supply there. Even tourism is not happening there. So that's the motivation behind this project, to create a standalone microgrid in these islands, and somehow make utilize of those space, at least for tourism, or maybe establish an industry. And that's the motivation behind that, right? So we can of course go with the diesel generator, but again you have to transport the diesel, the fuel cost, fuel transportation, and CO2 emissions. So that's not a big interesting solution, or a viable solution, right? So overall, this is not only in and around Singapore, but in the entire world. There are some situations like this where if you want to extend the existing grid, it is going to be a costly affair. So if at all you want to extend the grid for greater than 3 kilometers in hilly area and greater than 7 kilometers in plain, will be comparable to solar powers. That means the cost of right of way will be more or less equal to just buying a solar panel and installing a setup. But again, buying a solar panel cannot give you 24/7 power supply. At least with a battery backup, you can afford that, and you can say it is at least renewable, right? So That's where like still standalone AC microgrids will play a major role, right? So the motivation is very clear. Difficulties in extending the grid, and standalone microgrids is one of the option. But the problem is, if for example solar is available from 6 o'clock to 6 o'clock, just to be like more optimistic, 6 to 6, and wind maybe or may not be available throughout the day, and diesel generator is definitely required, like we can't eliminate that. And in future, if at all the cost of e- expanding your existing grid is possible, then you can also incorporate that. So we should have immediate solution for the current situation. At the same time, maybe a futuristic situation, if at all something happens, then we should accommodate that. It's not like you replace everything and come up with a new one. So we should have a little futuristic view as well, and that's where we are proposing this solution. So what is that we are planning here is, we are planning to have a microgrid which is islanded, which we don't have a strong grid there. So we have wind and PV or battery. Okay, so I would say the PV comes here and goes to the battery. Okay, so when I say battery, I'm talking about PV as well. You can integrate PV here. Okay? And diesel generator, because if there is no PV, there is battery backup is not there, and there is no wind, then at worst case, at least for some critical loads like hospitals and street lights, we need a minimum backup, and that is where we need to go for worst case scenario, and that is where diesel generator comes into picture. So we categorize the loads into multiple categories like single phase, three phase, linear, let's say critical and non-critical loads. Okay, critical loads, which the power supply should never get interrupted, like hospitals. Okay, we can't afford even a single glitch of power supply sometime. And non-critical loads, like your home applications or maybe air conditioning system, you can afford, even if it goes, you can afford that, right? So we can categorize that into different loads. So now, in case if at all there is possibility, we can integrate utility grid in future. Okay, so this is not now, but in future, if at all you want to make it as grid intertie or grid interactive, then we should also able to accommodate that, and that's the idea, right? So how to do that? So, for example, if you have only battery energy storage, then what you do, you use your so-called VSI. This is called the VSI, voltage source inverter. You can make your own grid. So you form the grid. Okay? You form the grid, and you can supply to your critical loads and non-critical loads, because now one is there. So it is very simple control scheme. You just give modulation index and you can maintain. Then if the grid comes in future, then what will happen? Grid will take care of voltage and frequency, and the so-called VSI will take care of how much P and Q it can support. Okay, so when I say VF, it is grid forming. When I say PQ, it is grid following. Right. So now, if the diesel generator comes into picture, then what is the problem? Problem is, yeah, diesel generator can take care of voltage and frequency, and this can still go into PQ mode, but there are some problems. Okay, and that problems we are going to discuss in a while, but fine. So when the diesel generator is there, you can make the diesel generator maintain voltage and frequency, and let the voltage source converter go into grid following mode, let it be in PQ control, right? Now the wind converter comes with a power electronic converter, wind generation with a power electronic converter. So that means again this is a VSI. It can also control its voltage, frequency and beta. You can control them. Okay. Here also another voltage source converter, you can control them. So these two guys can interact and they can adjust their voltages, frequencies, and theta, and they can coordinate and feed the load. That's not a problem. But if you don't have a power electronic converter in the grid, in the wind turbines, so that is what our proposal, like why you should have so many power converters. Can we eliminate at least one power converter and manage the show? And that is where our invention comes into picture. So what we are proposing like, if I have one smart guy in the system, I can manage this particular setup, and that is what we are going to see. Right? If you have power converter for every guy, then it is very simple. But buying a power converter for everything is a costly affair, and that's where we want to eliminate that. But still, we should meet the requirements. So our requirements is, at any cost, there should not be any interruption to the critical load. Okay, and there should be someone to maintain this grid, someone to maintain the so-called voltage and frequency, and the others should be in PQ mode or grid following mode. But whenever there is a changeover happens, it should have a smooth changeover or smooth transition should happen. Like diesel is going off and wind is coming in. Wind is going off and diesel wants to come in. So all this transition should be much, much smoother, and that is what we are going to see now, right? So another mode, when you have wind generation, when you have battery and diesel, so what can you do? So now what can I do? I can ask diesel generator to make the grid. The PQ will be here, and this is also will run in PQ. But there is no power electronic converter here. What can it do? So basically, this can be regarded as a weak grid, and it just follow once it is synchronized. Okay? So this is a weak grid. What it will do, once it is synchronized to a strong grid, it will follow that. It will follow that. As I told you in the beginning, it can be influenced. Their voltage, frequency, and theta can be influenced, and you can make it them same as the main grid, but the effect will be there will be a change in P and Q. The amount of P and Q it exchanges will vary, but you can influence them. So there is no need of converter here. So you can eliminate a power electronic converter here, right? So now in this case, this is the strong grid. As I told you, this is the smart grid, and this is the weak grid. Instead of diesel, if somewhere utility comes into picture, then diesel generator will be turned off. This guy will become the strong grid, and this will maintain the voltage and frequency if at all there is a grid comes into picture in future, and rest of the can remain same. Okay? So that's the idea behind a standalone microgrid, and let us see now how can we do that. Whatever I said in the modes, how exactly we can do that, right? So it is very simple, a two machine theory. So if at all you want to exchange P and Q, all you need to control the voltage magnitude and delta. And this is what we already know, because based on this simple formulas, two formulas, if at all you want to exchange P and Q, for example, if you want to exchange Q, then your voltage should be higher than the PCC. But you want to give power like P positive and Q positive, P positive and Q positive, then this is the situation. So your battery voltage or your smart grid voltage should be higher than PCC, and it should be leading. It should be leading, right? Similarly, you can operate your so-called smart grid in 4 quadrants. Okay, so in 4 quadrants, that is what you can do with this, right? So now, what is the problem here? The problem here is, if it is a machine-based power system, a machine-based generation system, your P is linked to frequency your Q is linked to voltage. That everybody knows. We all know this. But when you have a converter based generation, like let's say voltage source converter, then this relation is not valid. Your both P and Q is still linked to the voltage. Your frequency is decided by your modulation index, so that will never get affected. Okay, so that is where the tricky part. So when you bring in machine based grids and converter based grids, you can't strictly follow the so-called VB or voltage is linked to reactive power and active power is linked to frequency. That is only for machine based generations, not for converter based generations. Okay. And that is where so many converter controls are coming now, like which can imitate the grid, which can imitate the machine based grid. And that's where so many papers you can find in the literature, right? So now what we are doing is, irrespective of that converter based or whether it is a machine based generation, if you control delta, you can control P. Whether it is linked to V or linked to F, I don't care. Yes, all I want is I want to control delta so that I can control P. So then I can control modulation index so that I can control the voltage, and it may control P or Q or anything. So I just focus on these two variables, and that is where I'm going to start my control strategy, not entering into ABC to DQ modes or something, but we enter into a simple uh, load angle or delta control or modulation index control. Okay, so that's our idea. So as I told you, if it is the only voltage source converter feeding the loads, the control will be very simple. You bring in your own reference sine wave and make it phase shift by 120 phase shifted 3 sine waves, and it will act as a reference and it will maintain the grid. And you maintain little closed loop so that you get a sinusoidal voltages with fixed voltage and fixed frequency, and you can maintain the grid. It's very simple control, right? So what will you do? Whatever may be the changes, you always try to maintain the voltage magnitude. If there is a load changes, there will be a drop in the voltage, and you try to compensate with a simple PI controller, and PI controller output will give you a modulation index. That's it, right? So now, if at all there is a grid coming into picture, so what will I do? Grid will take care of voltage and frequency, and my battery converter has to enter into PQ mode. So what will I do? I was in this mode. Then I'll switch over to a different mode. That is, what is the active power that I should control and what is the reactive power I should control. So the active power PI control will give me delta, and the reactive power PI controller will give me M. So this delta will go and reflect here, and this M will go and reflect here. The same modulation strategy, but delta gets updated because of the PI control of power, and M gets updated because of the reactive power control. Right? So initially, what was there? Only one closed loop control was there because there was only one source. And now grid comes into picture. So I change the mode. My mode is now delta. I won't decide. I will decide by this so-called PI controller, and modulation index I won't decide, but it is decided by the Q control, that is reactive power control, right? So now if the diesel generator comes into picture, what will I do? I'll do the same thing because the diesel will be acting as a strong grid and my control strategy will be same. So I update delta and I update modulation index by using the same two closed loop controls. Okay, now other situation when wind comes into picture. So when wind comes into picture, what will I do? I will adjust my voltage and frequency so as to match with VW and FW theta W. Okay, then I'll go and sync with it first. Okay, because this is a weak grid, it has its own VW, FW, and theta W. Then what will I do? I slowly adjust my battery voltage, battery frequency, theta B, and I adjust this because I can control them. I can control all this. So I'll adjust and make it somewhere close to this and ask it to close the breaker. Once it gets connected, it will follow this. This will follow the battery converter. So just for interaction, I adjust this by using a so-called closed loop controls, voltage closed loop control and frequency closed loop control. Okay, and what is my reference? My reference is FW. Here my reference is VW. Current wind velocity will give you some voltage and some frequency, and then it cannot adjust because it is controlled by wind. So now what will I do? I will adjust my voltage, my frequency. When I say mine, I'm talking about the battery. Okay, it will adjust and go and ask the wind to integrate first. Okay, let us sync first. Once you get synchronized, then what will you do? You remove frequency control. You remove frequency control. This is no more required because it will follow. The wind will follow them. Then this will now becomes only maintaining a constant value. So this VPCC, it was VW, it will go equal to 415 volt now. Okay, so that's how it changes. So now what will happen? If there is a change in wind after the synchronization, whenever there is a wind velocity changes, if wind velocity changes, because of change in wind velocity, it will get reflected in either voltage or frequency. It will get reflected in voltage and frequency, and that will get reflected in finally the P and Q that is coming from the wind turbine. It is coming from the wind turbine. So it will get reflected in terms of P and Q. And it cannot influence the voltage and frequency, which is maintained by the voltage source converter. Right? So just for synchronization purpose, I do some work, meaning I lay a carpet for the wind turbine to come and join. Once it joins, it will follow the battery. Right? So after joining, I'll go into a simple control mode, that is voltage control mode. Right? So this is what happening. So now finally we have seen all the control schemes. We have seen all the control schemes. So wind to come in, what I am doing, I am helping the wind turbine to come and join the grid. So I am saying that as a grid supporting mode. Okay, I am supporting wind turbine to come and join because it doesn't have a power electronic converter. It has a power electronic converter, then you don't have to do that. That converter will do that. But if you can do that, why to buy another converter? Okay, so we eliminated this. That's the novelty here, right? And we are managing everything with a single converter. Now, if the diesel generator comes, again, it can control its voltage and frequency. It can control its voltage and frequency, VD and FD. But theta D, it cannot control. Theta D, it cannot control. But who is maintaining the grid now? Only battery is maintaining the grid. So battery PB, battery frequency and phase of battery is what there here. So now what will I do? I control only this and make it equal to the theta D. I make theta B is equal to theta D, then diesel can join. Diesel can join. Another support, small support. I don't have to change VB, FB because in the previous case what I did, I changed my voltage to VW, frequency to FW and theta to theta W. Now I don't have to do that with diesel generator because diesel generator can do something by using its governor control. It can adjust. Okay, so the VD, FD can be controllable. theta D cannot be controlled by diesel generator. So what will I do? I'll control the battery converter and change the theta B to theta D. Now diesel generator can come and join the grid. Okay, so once it joins, then I leave everything to diesel generator. Wind will go into PQ mode after joining, and battery will also go in PQ mode. The diesel generator will take care of the grid because it has some controls already existing, so I don't have to do anything. All I have to do is I have to somehow bring in and join the grid. That's what I did, right? So this is where all the control strategies comes into picture. I change over from one mode to another mode. At the end of the day, what I'm trying to do, I'm just trying to control M and trying to control delta. By controlling these two, I can manage integration of diesel generator, PV or battery, or PV plus battery. There can be PV here, which is connected to the battery, and wind. Everything, all the three. If at all there is a grid in future, if there is a grid coming into picture, yes, that is also can be managed with a simple control scheme, right? So now we have seen different modes separately. In every mode, what we can do. But now my question is how to do or what to do if there is a transition. What do you mean by transition? Let's say wind and battery are working together. We know how they integrate. After integrating, they are working together. Now wind has to go. Why we have to disconnect wind? Because the speed of the wind has reduced, and the wind generator may start operating as a motor instead of operating as a generator. So it is unnecessary loading the battery, so I have to disconnect it. Okay, how to bring it back? We know how to bring it back. Battery will adjust its voltage, frequency and theta so as to match with the wind, and then we combine that. We know. So now if battery is feeding the load, battery is alone feeding the load. Now battery is about to drain, and now I should take a call. Like someone should support. Wind is not there, so obviously I should call for diesel. So I should bring in diesel. So how to bring in diesel? Very simple. VD and FD they can somehow manage. Theta D cannot be managed, so I'll make theta B equal to theta D, and they can join. Right. Once the diesel comes in, maybe some issue or something need to be done with the battery maintenance or something. So battery can go away. Why? Because once the diesel joins, diesel can maintain the grid and diesel can alone can operate. Possible. So now if the diesel is operating, can I bring in wind? Can I bring in wind? Because diesel can control VF, or I would say VD and FD. Theta D cannot be controlled. Theta D cannot be controlled. But to bring in wind, I need to control all the three. I need to control all the three. So that is not possible. There is a possibility you keep on adjusting frequency for quite some time, and somewhere it will match. Somewhere it will match. There's possibility, but it is not allowed for now, and that is where you can't do that, right? So now if at all you want to bring in this mode 4, what you need a battery guy. So first you go here, ask the battery, hey battery, can you just come and help me to bring in wind? So it will, yes I can support you. Then it will go there, get the wind, and then battery will go after making diesel and wind together. Okay, so from 5 to 4, if at all you want, you need battery. So the path will be 5 to 6, 6 to 3 and 3 to 4, right? So this is how all the modes and mode transitions can happen, and this is not just for argument purpose, but this is what actually happening in the real system. wind is oscillating, battery charging may go up and down. Okay, and diesel generator should act as only as a backup, right? So these are the modes and mode transitions. So this circles are modes and these arrows are transitions, all the transitions. So in any mode it is stable, but how to make the transfer easy, that is what we did here, and as I explained. So let us see some situations why you need to go from one mode to another mode. For example, if you take only wind, if you have only wind without power converter, it cannot maintain constant voltage and constant frequency. So it is uncontrolled operation. We know that as wind changes, voltage changes, frequency changes, so you can't maintain constant voltage. So battery is not operating, diesel is not operating, dash dash. So now if wind and battery is there, yes, then what will happen? Wind will be in PQ mode, battery will be in grid forming mode, either charging or discharging, diesel is not operating. All the three are there. Then what will happen? Wind will go into PQ mode, BES will support grid, support the wind to bring in. After that, diesel generator will make the grid forming mode, and this will go into PQ mode after making the transition. After making the transition, it will go into, or it can stay with only Q control. Either it can charge or discharge. Okay, what is PQ mode here? P is nothing but either charge or discharge, right? Charge or discharge. So similarly, all the modes can be visualized there, right? And what are the event that will cause this transition? What are the events that will cause this transition? These are the events. If the wind velocity is greater than cut-in speed, you need to do something. If the wind velocity is less than cut-in speed, you need to do something. If the state of charge of the battery is very low, you need to do something. If it is very high, you need to do something. Okay, so this is where you need to make multiple transitions, right? So we have carried out some simulations, then followed by experimentation. um, in between, if there are any questions so far before entering into the results, I would like to take it. Sir, can someone help me to see if there are any questions so far in the chat? I hope I'm audible. Sir, can I continue? Hello? Okay, looks like no one is available. Let us continue. So this is the flow charts, how to take a decision. For example, I'll just talk about few flow charts, and then you can figure out what exactly it is. So first, to begin with, our battery converter plays a crucial role here. So our job is to first check whether battery has enough charge or not. So what is that enough? So that enough is, we decided like we need a minimum charge. So if SOC is greater than something, then you start the battery converter, right? So you should always check this now and then, right? If it is not already started, then you should start battery first. Okay, so without battery, it is tough. So we always recommend to start the battery converter in the beginning. You can start diesel generator first. That's not a problem, but uh, then synchronizing battery is also not a problem. You can do that. Okay, so we started with the battery. So So then we'll see the wind. We'll see whether the wind is able to generate or not. What is the current wind velocity, and that wind velocity, is it able to generate something? If it is there, then we'll check whether battery is already operating. Yes, it is already operating. Then you start and synchronize the wind generator. So how to do that? How to do that? So first we need to adjust the battery voltage, battery frequency, and battery theta to match the incoming wind, and that is what we are doing here. Once it is done, you synchronize. Then based on the synchronization, based on the power that is coming from the wind, and based on the state of charge availability, we'll take a decision whether the critical load should be off or on, okay, or non-critical load should be off or on. So accordingly we'll take some decisions based on power balance, just based on power balance. This conditions you can decide. You feel like, no, this non-critical load should be considered as a critical load. Yeah, it's up to you. Fine. So now, what is the other one? This is the start of BES is very simple. Start synchronizing is very tough process. So how we do that? So as I said, first you need to see voltage is building up, and then we need to adjust the dump load of wind so as to become a reasonable close values of nominal, right? So as I told you, a theta VB, FB, and theta B, we are adjusting so as to match the wind, so as to match the wind. But if the wind is too far, like it is 550, your nominal is 415, which is not allowed. So what we do, we use dump load, and somehow bring those voltages and frequencies close to certain values, and then we start adjusting the VB, FB, and theta B. So again, adjusting theta B is a tricky part. You can't simply change the number. It should be slowly changing. You can't simply change from 10 degrees to 90 degrees, or 10 degrees to 40 degrees. You can't change the number. It should be a slow process. If you change that, there will be a problem, right? So you should not change abruptly, but there's a slow process. So now once it is done, all the things are matching, you connect it, and then you bring it back nominal voltage and nominal frequency. And at this stage, the wind will start following you. Wind will follow. Okay, so that's how we do the synchronization, right? And this is one simulation which shows you the synchronization is happening. Okay, these are all the cases that we simulated as well as experimented. So what we did, simulation starts with the battery, then battery will maintain some voltage and some frequency. Then there will be a critical load which is always connected. Then wind rises at 4 seconds. Then we bring in dump load and somehow make wind velocity and frequency close to the nominal values. Then we use the battery converter to adjust its voltage frequency and start the synchronizing process. So this is all a synchronization process. Once it is synchronized, we bring it back to normal, remove the dump load. Okay, we have to remove the dump load, or you can shift this here. After synchronization, immediately after synchronization, you can remove the dump load. That is also not a problem. You can choose based on your power ratings. Then if the wind velocity further rises, then you can power more loads, or you can decide whether to charge your battery or you want to power other loads. It is up to you. So you can decide either to charge the battery or to supply non-critical load, right? Then if the wind velocity rises, then you can further increase. If the wind velocity decreases, disconnect the load. If the wind velocity is very very small, then this wind turbine will start acting as a motor. Then it is minus V. Then you have to disconnect it. We have to take a call and disconnect, right? So we did this in the experimentation as well. This is our experimental setup. We have a critical load, non-critical loads. This is the battery converter, right? And we have the synchronization relay just to cross-check physically. And we use this in DSpace control. And this is the battery emulator. And this is the dump load for your wind. And this is the wind setup, self-excited induction generator with some capacitor banks, right? And these are some meters. We use the power quality meters. These two are meters, and other meters here and there, right? So what we did wind and battery. Diesel we didn't bring in because if you can show that it is working with the wind, it will obviously work with the diesel. So well, we didn't do that. Fine. So in the lab also we did a single run everything. So battery is already running here. Battery is already running. VV. Then wind velocity rises. Dump load is on. Then synchronization happens. All this V, F, theta will get adjusted and get synchronized. Then we bring it back to nominal values. Dump load is turned off here. Wind velocity rises. Then because we have more power, we turn on non-critical load, right? So when wind velocity goes down, we turn off non-critical load. And wind velocity goes further down, then we go for synchronization, that is desynchronization. Okay? So I'll show you a few results where the synchronization is about to happen. So you can see this is the battery part, all are 450 hertz. Wind before turning on dump load, it was 441 and 52 hertz. To bring it down, we turned on some dump load, and you can see it has come down to 387 and 50.6. Okay, so now we adjust battery, which was 450. Now we adjusted these values so as to match this, right? And because some drops here and there, so we maintained a little higher than this, and you can see it was sinking, almost sinking. Then we saw everything is matching and we synced it. From here the synchronization happened. Then after that we bring back to nominal values, and all are same now, right? So now if you see this, everything is synced. We adjust the frequency, we adjust uh, voltages. Accordingly, the P and Q will get changes. P and Q will get reflected. Right? So this is where I think this is the situation of when the non-critical load is on, or I would say something is negative. That is, battery is charging. It is oh no, I think wind is started acting as a load. Wind started acting as a load, so we have to disconnect it. So now we will try to disconnect it. So when we disconnect, you can see they are going apart. They're going apart. This desynchronization happens here. It was synced here, and here it is desynced. That means the breaker is open, right? So this is what we did. But again, when you want diesel to bring in, then the flowchart will become little more complicated. Same thing. So you should always check the battery charging at every few instances, at least if at all something majorly is happening, or you should make that as a major concern, because if without battery converter in this setup, it is very difficult. So you should always make sure there is some amount of charge is left. If charge is going down, then immediately you should ask diesel generator to switch on. Okay, once the diesel generator is switched on, maybe you can use the diesel generator to charge the battery, right? So if we are already operating wind, we bring in, we sink in. I hope you know already, like what to do. For diesel, it is very simple. Voltage and frequency can be more or less adjusted by the diesel, but the theta alone needs to be adjusted by battery converter. Right? So that's how you can make all the flow charts. But again, remember, you can't simply change the theta abruptly, but you should have a slow variation. That's the only thing needs to be taken care of. Right? So we did multiple simulations, and all the results are there in our publications. Right? So again, when it comes to the control strategies, whatever we followed, we are not saying that's the only solution. You can come up with multiple solutions, but you know, in our situation, we decided to use the renewable energy as much as possible and bring in diesel only if they don't have any option. Okay? But you can decide like what should be your priority, what is your customer is requesting, or what your industry partner is requesting. Accordingly, you can fine tune. Only thing is you need to remember all these three concepts like strong, weak, and smart. So if you know their performance characteristics and you can bring in any kind of innovation or any kind of novel control strategies into the system and come up with multiple case studies or multiple scenarios, and then you can come up with your own strategies how to handle that situations. That's all we did, and that's about today's topic. I thank you very much for your attention, and apologies if there were any kind of miscommunications or some interruptions in the audio or clarity. Right? Thank you all. Um, yes, sir. Are there any questions?
Sir, thank you very much, sir, but no queries from participants, sir.
Okay.
Very informative session, sir.
Thank you, ma'am. Sure.
Sir,
Shall
can
I?
we close the session, sir?
Yes, ma'am.
Okay, sir. Today, I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Dr. Dastagiri Reddy Garu, for accepting our request and for giving such a wonderful presentation on smart integration of renewable energy technologies at the standard alone AC microgrid and making this session meaningful and interesting. Thank you very much, sir. I would like to express our profound gratitude to our correspondent madam, director madam, MD sir, and principal madam for uh, for their constant support and encouragement. Thank you all. Finally, at the end of this session, I would like to thank all the participants from the various institutions for their glorious presence. Thank you, everyone.